Okay, well, if you're like me, your attention span is about 1 minute at this point. So the talk I'm giving hopefully will not tax that. So everything I will say will be in 1 minute snippets, and okay. So first, this is what I'm talking about is joint work with Justin Gilmer, who is a student of mine who recently finished, and Michal Kutsky. And so here's the outline of the talk. I'm going to tell you a game and a conjecture. I'll tell you why it's interesting. I'll say something about why you might believe the conjecture, and then I'll say something about why you shouldn't believe the conjecture. And then after this, you...
Right? I mean, a minute later, we don't remember number 3. You can tell us a completely different story.
That's right. So why you should doubt it, okay, but then at the end I'll say something about why, despite the fact you should doubt it, it still might be true.
6.
Okay, so what's the game? So here's Alice. Here's Bob. And so Alice is going to get his input, a random permutation, which we'll think of as just a sequence of numbers from 1 to n, so sigma 1 through sigma n, and also a bit b in 0, 1. And Alice is going to get these, this is going to be streamed. She's going to get sigma 1, sigma 2, up to sigma n, and then she'll get b. And she'll send a message to Bob. And the message will be constrained in a way that I'll describe in a minute. Okay, so Alice is going to prepare a message, send the message to Bob, and the message will be a vector, which I'll call gamma. 0, 1 to the n. And Bob will look at the message, and Bob has to output. So Bob looks at the message and outputs a subset of 1 through n. And the requirement of the output is that sigma n, the very last element of the permutation, should be a member of the set. And the cost is the size of the set that. So the one thing I haven't told you is what's gamma. So what's Alice allowed to send to Bob? So gamma you should think of as it's an array indexed by 1 through n, and it starts empty. Now I said that Alice receives this permutation streamed, and sigma 1 arrives, and think of sigma 1 as an index into the array. And Alice, she can write a 0 or a 1 in that position at that point. And then sigma 2 arrives, and she can write 0 or 1 there. Keep doing this. Now, but there's one catch. When sigma n arrives, Alice doesn't get to choose what to write there. When sigma n arrives, she must write the bit b, which is this last bit that's sent in the stream, has to get written there. Okay, that's the game. Okay, as my daughters would say, if that's a game, remind me not to come to a mathematician's party. Okay, but this is the game. And that's the cost and the value of the game. Well, so Alice has a strategy. And, Alice and Bob have a strategy. And you look at the worst case cost. So once Alice fixes a strategy, which is how she's going to respond to each arriving sigma I, then the cost is the worst case over J.
So we can think of sigma and B being sent by an adversary. Who knows the
strategy. So, so we'll write Vn for the worst case cost of the best strategy.
Just to make sure, both Alice and Bob are deterministic.
What? Everything's deterministic, at least at the moment.
So Mike, just to check that I understand the problem, so you can solve it on average with log n cost, or what is it?
Well,
Does it make sense to just write down the value of sigma n?
but you don't know sigma n.
Alice knows.
Sigma 1 through sigma, no, so this is important, this is important, right? So let's, now that I've said it, let me review the important parts. Sigma 1 through sigma nb is arriving as a stream. So you get sigma 1 and you must commit yourself to what you write in position sigma 1. Then you get sigma 2 and you must commit yourself to what you write in sigma 2. So if it weren't for this bit b, I mean, here's the strategy. You write 0 every time and you write 1 at the end. Okay, and then Bob knows what the bit is. You look.
It's still like 0 all the time, and then half the time.
Yeah, but it's worst case. It's worst case. It's worst case.
Oh,
It's worst case. Yeah, that's right. But yeah, if all right. So now here's a conjecture. Now, I'll say, some people use the word conjecture to mean something they really believe. And other people use it to mean something that, and I've had debates about this with what should conjecture mean, but, well, to me it means an interesting question that would be nice if it's true, but I don't necessarily believe it. The conjecture is that that there exists a delta greater than 0 such that Vn is at least n to the delta.
That exists or not exists, depending on who look at it.
That's why it's
There exists. Okay. So let's see. So that's the game. That's the conjecture. Why consider it?
So can you give us an example of a strategy?
I will. In number 3. So there's an old conjecture in Boolean function complexity called the sensitivity conjecture, which has well, it's interesting. It appears in a paper of Nissan and Segedi from the early 90s. I don't know. I don't remember which year. But they don't state it as a conjecture. They state it as a problem. And it became known as the sensitivity conjecture. There's a really nice survey article about, a whole bunch of different reformulations of it. It's called Variations on the Sensitivity Conjecture, which was written by a group of graduate students at University of Chicago, and I should have their names, but I don't have them handy. But here's one version, which is my favorite. So let's F is a Boolean function, or let's say Boolean function f. So the sensitivity of f at x, here's x and 0, 1, is just equal to the number of neighbors y of x, and these are just neighbors in the Boolean cube, such that f of y is different than f of x. So the number of bits that you could flip, which would change the value, and then the sensitivity of the function is just the maximum sensitivity. Maximum over all inputs. So, for example, the AND function, which is 1 at one point and 0 everywhere, has sensitivity 0 almost everywhere, but there's one point where it has sensitivity n, so the sensitivity is n. And there's a talk at 5 p.m. Ankit Garg. Here's the title. I'm about to erase it.
Room 160.
No offense, Ankit. And then the degree of f is just the minimum degree. Well, the Fourier degree, or of a real polynomial E agrees with f. So it's known that the sensitivity of x is at most the degree of x cubed, maybe squared. I don't quite remember.
SF.
I mean the function.
Deck F.
Oh, s. Sorry. Let's try that again. The argument is f, not x. The degree of f, the sensitivity is bounded above by some polynomial in the degree. I don't really care what the number is there. And the conjecture is there exists a k such that degree of f is always bounded by the sensitivity to the k. Let's say
Is it that universally for all functions or?
for all functions. What? For all Boolean functions. And so now here's a proposition which says that if there exists a Boolean function of degree n, and sensitivity S, then Vn, the value of this game, is at most S. So if you had a Boolean function where the sensitivity was really small, you could use it. Essentially, that function can be used to give a strategy for Alice and Bob, which has very low cost. And in particular, so if you could prove that the game has high cost, then you get as a consequence. So it implies a sensitivity conjecture. Now, I want to mention, so when I posted the abstract of this talk, I got an email from Andy who said, I didn't say what the game was, and he described this game that he'd been thinking about for a year, which turns out to be the same game. And and he has, essentially the same proposition. So that's, I just wanted to mention that there was an independent discovery of the same question. What? Andy Drucker. Okay, so good.
Related to these Cauchnell-Wignerson games? No. Is this related to the Cauchnell-Wignerson game?
I don't think so. So, I've got not that much time, so I'm not gonna prove much. The proof of that takes 3 minutes, 4 minutes, but that's more than the 1 minute that I promised the attention span requires. Okay. So why believe it? Why should you believe the conjecture? Well, one is a hopeful reason, like, if the conjecture is true, it implies a sensitivity conjecture. So that's one reason to believe it. Let's think about, what would be a good protocol? Okay, how good a protocol can you get? So I switched to the sensitivity conjecture. Now I'm switching back to the game. Forget the sensitivity conjecture. Let's remember the game. What's the game? The game is Alice is getting streamed a permutation sigma 1 through sigma n and a bit b. She gets to write in a vector, but the positions she writes in is in the order governed by the arrival of the permutation. But she doesn't control the last bit. The last bit is controlled by the b that comes in. All right. So, okay, here's a slightly non-trivial protocol. You write 0 for the first n over 2 time steps. Okay? You write 0, and then you write 1 for the last n over 2, but you don't control the very last one. But now Bob looks and he says, how many zeros are there in the vector he sees? If there's n over 2 plus 1 zeros, he knows the last bit that was written was a 0, and he can output the set of zeros, which is a set of size n over 2 plus 1. And if otherwise, he outputs the set of 1, which is a set of n over 2. So there's a protocol which gets n over 2. How about a better protocol? Okay, so take the bits, your vector, and break it up into chunks of size square root n. And now Alice's protocol will be, when sigma I arrives, if sigma I is not the last thing to arrive in its block, then write 0. And if it is the last thing to arrive in its block, then write 1. So, it'll be 0, 0, 0, 0, 0. Okay, and then by last thing, I don't mean last here. I mean the last arrival in the block. Okay, now what does Bob see? Well, Bob is either going to see one block that's all zeros. That's if the last bit written is 0. And he knows that the last thing is in that block, so he outputs that block. Otherwise, he sees 1, 1 in every block. in which case the output's that. So there's a protocol of size. So that shows that Vn is less than square root n. Okay. So we know this, maybe 0.999. I'm not sure. We can do better than that. But it's not so easy to do better than root n. I don't know anything better than this. Okay. So that's one reason to maybe to believe it, is that nobody knows. And by now, I've talked about this at a few places. People have thought about it, and nobody's beaten this.
What is the lowest sensitivity that we know of for a Boolean function?
Say again?
What is the lowest sensitivity that we know of for any Boolean function? Or maybe for 7?
Yeah, so we know a quadratic gap between
So root n is the...
Right. So this so if you there is this thing actually comes from a Boolean function. If you take the tribes function, then that's a function of degree n and sensitivity square root n. And if you apply the proof there to this thing, which says that if you give me a
Root n times of root n each.
yeah, and if you just apply the proof, which I didn't show you, then you will get this game. I mean, you'll get this strategy. Okay.
Improvement is not from is it from a Boolean function again?
Say it again.
This improvement that you have,
Yeah.
is there a function underlying it?
No. No. And that's so we don't know that things go the other way. It could be the most uninteresting thing that could happen is that the conjecture turns out to be false, but it doesn't give a counterexample to the sensitivity conjecture. And if I were to bet on what's true, maybe that's what I think is going to happen. But okay. So fine. The other reason why should you believe it? So, here's an information theoretic intuition about what's happening in this game. When I write the kth bit, I'm trying to, Alice writes the kth, gets sigma k, writes the kth bit. So she's trying to convey some meaningful information about what's the last thing that's going to arrive. But at that point, all she knows is that it's one of n minus k things. So, what she writes can't be very informative about that. And if you sort of follow that reasoning and you think about information theoretically, you can sort of get some estimate to how many bits can Alice tell Bob about. And you get something like a harmonic sum, which is natural log of n. This is very heuristic. Natural log of n, but she needs to convey log base 2 of n bits. So there's a gap, and that should reflect. And that was so those are the reasons to believe it. Now, why should you doubt it? So let me tell you 3 conjectures, 3 strengthenings. So first strengthening, one is consider sigma and b uniformly random. And now instead of looking at worst case, you look at the average case. So you look at a strategy, and now you just charge the strategy, what's the average? And if you, like the strategy I gave, the particular strategy we gave, which was root n, well, it's always root n. So the average case is exactly the same as the worst case, because everyone is root n. We had the strategy where if you write 0 every time, then with probability of half, you win. You only costs you 1, and with probability of half, it costs you n. So that'll have average case n over 2. So if I write v bar n, so, we can have another conjecture prime, that v bar... Okay. So that's a conjecture. Now, here's another... If you think about that, and if you think about the information theoretic intuition, then you can forget about what Bob outputs, and you can just say, well, what does Bob learn? So what I would like to look at is, what is the residual entropy of sigma n given the vector gamma? How much entropy is left if in this, now we're still in the random setting. So you fix your strategy, you know, Alice follows it, Bob looks at gamma, the distribution on sigma and b, and the known strategy for Alice induces a distribution on this, and you can just look at what's this. And so it's reasonable, conjecture double prime, and Andy also conjectured this one, to conjecture that this is greater than some epsilon log n for some positive epsilon. So now, and it's easy to see that this conjecture implies this one. And third conjecture, well, if you think about the intuition, you could play the same game, except you allow Alice, instead of writing a single bit, she writes 2 bits at each step. Same question, right? So you just say that the Alice's alphabet size is, let's say, 1 up to k, where k, think of k as a constant. And you could ask, you know, what happens here?
Sorry, in this case I was thinking of B as 0, 1, or is B also in the same alphabet?
B is in the same alphabet. Yeah. Okay. So now the bad news is, well, this is false, and this is false. By false, I mean, so here I'll say, let's say, just stay with the worst case one. And here, so that is to say, there is a
3 isn't a statement, it's a phrase.
Okay, so then define Vn super k, which means the value of the game, the worst case value of the game when the alphabet size is k. And then you might say that this should be at least n to the delta for something.
Delta K. Delta sub K.
Okay.
So to say it's false means there exists a K.
Right, so what we know, so it turns out Vn3.
Sorry, Mike, for every delta,
Well,
for
here,
K, there is a delta.
this is going to answer here that it's false.
No, you want, so it's free, delta can depend on k. I mean, in the conjecture, but it's false. So Vn3 turns out as order log n. There is a protocol, if you allow them an alphabet of size 3, in which the size of Bob's output set is only order log n. Okay, and this one's false. There is a protocol, this is back in the binary thing, in which this is less than epsilon some constant c log n.
This is with the uniform distribution.
With the uniform distribution. Okay, and this one we don't know. This is open. So in other words, it's very natural to pass to entropy, because we know how to prove things about entropy. But this is, you know, there is a protocol for this, but the protocol that has low entropy turns out not to have low expected cost. Okay. In fact, the expected cost, so the expected cost of the protocol is n over log n, or n over, it's big. Okay, but the entropy is small. Okay, and now my time is up. But I'm going to take one more minute and say why. So after you hear this, you know, the intuition was information theoretic, but the information theoretic statement is false. And also the intuition doesn't, well, you know, the same intuition would say that if you could write 3 symbols, how does that help? Okay, That's also false. Okay. If you look at the protocols that provide counterexamples to this, they satisfy the following property, which is this, that in the protocols, to specify what Alice does, so, Alice has filled in some bits somewhere, and then I arrives, sigma I. This position, let's call it position J, arrives. And her strategy says, well, I look at these and I decide, and maybe I also look at the past, and I just decide what to write here. And we'll call the protocol monotone if it has the property that if you're in a configuration where if J arrives now, she'll write 1, then later on, if some other stuff arrives and now J arrives, she'll still write 1. So once she decides to write 1 in a location, if it arrives, she never changes her mind. So that's a monotone protocol. And the protocols that provide counterexamples for both of these are monotone. However, the original conjecture we can prove is true for monotone. So, I don't know what to make of that. It just is. So, in fact, and we can prove it with square root of n in the case of monotone protocols. Exactly square root of n. The 0.99 square root of n that is non-monotone. Okay. So, all right. So that's what I have to say.
So you did add 6. When you say that when you go from monotone to non-monotone, you go from square root n to 0.999.
Yeah. Oh, there is a number. Yeah.
After all.
Yeah, that's right.
Can you say something about the proposition?
Can I say something about how the Yeah. I can say. So what I'm going to do is you suppose you gave me this Boolean function. So first of all, it's easy to see if you have a function of degree n, you can fix all but n of the variables and it'll still be degree n. So you can assume your function actually has exactly n variables and its Fourier degree is n, and it's got sensitivity only goes down if you fix variables, so it's still sensitivity s. So you start from this function, and now I'll use another fact, which is if you have a function of degree n and you pick a variable, then there's a way of fixing that variable so that the degree of the residual function goes down by exactly 1, right? When you fix a variable, maybe it goes way down, but one way or the other of fixing it only goes down by 1. So now you take the function, and Alice's strategy is this. She keeps this function in mind. When a variable arrives, she sets the variable in such a way that the degree of the function, when you fix that variable, goes down by 1. She keeps doing that. And then you just convince yourself that at the end, and then what does Bob output? Bob, at the end, receives an input, and he outputs the set of coordinates on which the function is sensitive, which is size at most s. And you just, then you can just check that protocol works.